Well, welcome back to another installment of Eric's Electronics. It's been a long time since our last installment in the repair of this Packard Bell Model 501 All-American 5 radio receiver, an AM receiver that, as I had mentioned before, has some sentimental value for me. This was the kind of kitchen radio that I grew up with, and so as part of my own personal project in terms of restoring this, I thought I'd take the opportunity to teach you some basic mid-century electronics in the process. So as we get into this, it's been a while, and so let me get you caught up as to what has been happening and a couple of other things that I've observed about the radio in between. So let's get started. So one of the first things you should notice is that the chassis here is a lot cleaner than it was before. And what I had done was actually take some steel wool, Brillo pads here in the U.S., and very gently gone over this. Now, as you can tell, I wasn't able to get everything, and I didn't really want to dig in because in using steel wool, of course, it leaves behind little pieces of steel wool. And those little steel fibers are very, very dangerous when it comes to trying to work with these variable capacitors, and if they get inside the workings here, the circuit, then that's going to be a problem, causing shorts and unexplained current paths. So the other thing I wanted to point out is what we have here is what's called a point-to-point wiring scheme. I think I may have touched on this briefly. And what's going on here is just that we have these components, like here's a resistor, for example, and it's just wired from this point to this point. Notice there is no insulation here. There's no insulation here. There's insulation here, so it's kind of inconsistent. So the idea here is just that, if you kept, as you were assembling this, if you kept the components, from touching each other, then you should be okay, and the air, the atmosphere would actually be the insulation, preventing any electricity from going from where it's not supposed to be. Okay, so as I get in here and start replacing these old paper capacitors, I'm going to, and as I probably will have to get into some of these, moving some of these components around, but I will put some insulation on some of these components as I dig into them. I'm not going to do everything, I'm just going to do the things that I'm going to touch, the components I'm going to touch. The next thing to point out here is that as I was looking at the schematic, I found something kind of interesting. Remember I had said that this little jack here was likely an external speaker? When I actually looked at it and looked more closely, I realized, first of all, this is connected to this capacitor over to the potentiometer, which kind of led me to think that it might be a speaker. But on the other side, notice there is no connection here. There is a connection to the chassis, but that seems to be, it's unclear as to what's going on there. So there's this capacitor here connected to this jack, which might be for an external speaker. But here's the problem. This capacitor and this jack do not appear on the official schematic. So that's kind of curious. So we're going to have to figure out what was going on there. I'll have to kind of study this a little bit more. I'm kind of curious as to what was going on. Again, we mentioned some components that we'll have to replace besides the capacitors. We'll have to replace these the resistor here, which is beginning to corrode. There's another capacitor here that's going to have to be replaced. And then we'll be getting into it. The other thing that we were concerned about was whether there was a problem with the non-polarized plug here, and whether there would be any danger of being electrocuted or getting a shock from the direct connection from the hot to the chassis, which is frequently a concern with these All-American 5s. Now, as I was looking at it just visually, there is no visually direct connection. It's possible that it may exist, but there doesn't seem to be any direct connection. Here's the line cord. It goes into the on-off switch, and then immediately goes over here to start its transformation from AC to DC power. So what we're going to do here is we're going to actually just test it, just a very simple static test, where I'm going to just turn on this ohm meter here. And you'll notice that when I touch the leads together, you may not be able to see it, but the meter does register that there is some current flow. So if we go and get the plug, and we grab one of the prongs of the plug here, you can tell it's got these nifty little holes here. First of all, obviously no connection here. When I touch the base, the chassis here, and there's no connection here either. There's no current flow. Turn this around, grab the other prong, and again, no current flow. Now that doesn't tell us everything, but it does tell us something. It tells us that there is no static connection between either leg of the power cord and the metal chassis. By the way, the thing I didn't mention to you is that this is on. The switch is on here. So what we still need to find out is, of course, what will happen when we actually turn the unit on. Now, in the meantime, I'm still going to replace this cord with a polarized plug and connect the neutral and hot sides to the appropriate side in the circuit. So that's going to happen. This cord will definitely go, and we'll make that right. All right, let's see. The next thing we're going to look at is the missing parts here, the tubes. Well, welcome to one of my prides and joys here. This is a Hickok portable tube tester. The tube tester was used to test vacuum tubes, and you would normally not have one of these unless you were an engineer or fairly serious enthusiast. If you wanted to test tubes, most of us would just go down to the local grocery store, drugstore, department store, hardware store, where they would have these units, and they would basically have the same circuitry here, but the unit would be about the size of a modern, freestanding ATM machine. It would have the charts up here. There'd be some marketing material up here, and then underneath would be the supply of the tubes. And if you tested your tube and needed to buy a replacement, some helpful person would come in and unlock the thing and get the tube out, and you'd buy it at the checkout counter. But what we're going to do now is we're going to use this tube tester. I'm going to show you how this particular one works. Tube theory is something we'll go into later, but I felt like we wanted to actually just get started here and get into it. You'll notice that it has several different sockets. So here's pretty large tube here and here, over here. The tubes that we are going to be testing are going to be using this socket. Notice this really small socket over here, and then this one, which is the pins are all in a straight line. Those were tubes that were being used in the late 50s and early 60s. They never really caught on super popular, but here it is. If those tubes ever came up with a piece of equipment that used tubes like that, I would be able to test them using this unit. So we'll get a close-up and we'll go through the process of how to use a tube tester. So now as we get started, you remember my little box for small things is right here. The tubes are inside. What we're going to do first off, we're going to turn the tube tester on. What we do is we just turn this on like so, and then the inside of the tube tester is going to be working. You can start seeing that the meter over here is beginning to deflect. And what we do, first thing, is we adjust this knob so that this needle for the meter is right up there on the line test mark. So we just kind of turn that up. And what we're doing here is we're actually adjusting the tube tester to normalize the line voltage. So now that that's set, we're good to go. The next thing we're going to do is we're going to decide which tube we want to test. So I just got a tube here, and we're going to take that one out. We're going to start with this tube. This is a 12BA6. It's very hard to read. As a matter of fact, even for me, the printing is pretty faint there, but that's what it is, a 12BA6. So we're going to put that in. And the first thing we're going to notice is that these lights underneath this hood, these lights, which may be difficult for you to see, are all on. If one of them turned off, that would indicate that there is an internal short inside the tube. So what happens now is we know the tube number, so 12BA6. So we go through here and we turn this little knob until we find the 12BA6. 12A, and then we're going to keep going on 12BA. Oh, there it is. 12BA6. And then what we do is, it's right here, and then what we do is we just set all these nice knobs and switches and stuff to these settings. The first thing we're going to set is the filament voltage 12.6. Tubes, in terms of their numbering scheme, are all pretty much the same. The first number is the tube filament voltage, in this case 12 or 12.6. The last number, in this case the number 6, indicates the number of elements, active elements inside the tube. So what we've got here are 12 volts of filament voltage, 6 elements inside, and then the middle two letters, the BA, is the manufacturer's distinction in terms of here's what it's supposed to do, here's its function. So we have 12BA6, the filament voltage is 12.6, the selectors are ET1, 5, 6, 7, and then 2. I just want to say that it really is as gratifying as it sounds to be able to, switch those little switches like that. That is actually pretty cool. The bias is 11, so we turn the bias up here to 11. The shunt is 72, so we turn the shunt up to 72. And then the function is A. So the function over here is A. And now, as we've turned up the filament voltage, the filament will begin to glow, and it may actually be able to see that. So then what we're going to do is we're going to now do the test. Now there are a couple of tests we can do. We can actually test the filament continuity, which is not going to be hard because we can tell the filament is working. So that's kind of a ridiculous test, but there it is. Yeah, okay, that's working. And then we hit the test button. Let's see how well this tube is performing. Oh, look at that. Very good. Very good. All right, I'm happy about that. All right, so then we're going to turn the filament voltage off and let the tube cool down a little bit, because that's what makes tubes hot, as the filament actually heats up. Yep, that's not so bad. For a 12 volt, it's not, these things cool off pretty quickly. All right, so then what I'm going to do is I'm going to go through and test all of the tubes for the radio and see which ones are working and which ones aren't. All right, what I wanted to show right now was an example of a bad tube. So this is not from the radio, it's actually from another project. And here we can see there are no shorts. Here this happens to be a 12AX7. We can look at the filament continuity, and it is not good. There's no filament here. As a matter of fact, when we look at it, you cannot see any nice orange glow here. That's going to be a problem right away. So this tube is bad. We already know the tube is bad. By the way, just go ahead and set it up here, and if we run the test, again, it's bad. So clearly, this one is no good. It's got to go. So that's one reason why a tube can be bad. All right, here's another tube, just to show you what a more conventional tube failure looks like. So this happens to be a 12AU7 triode, dual triode. Again, it's two things in one sort of packaging. So when we set it up here, you see no shorts. Filament is good. You can see a little bit of the orange glow there. And then when we hit the test, see how it goes down to replace? Clearly that's not right. That is not good. So that tube is bad. We can look at the other side of the tube and adjust that. That's going to be the 12AU7 on the second side, and that's going to be EV2 103 and 0, 24, same shunt, same bias, function is A, and that's all right. There we go. There we're set up. All right. So you can see how tube testers work, what it looks like when a tube is good, what it looks like when a tube is bad. And so I hope that is kind of fun for you. And yes, like I said, it's really fun to turn the knobs. That is pretty cool. Okay, so what we've seen is we've seen the progress on cleaning. We've pointed out what point-to-point manufacturing processes look like. We have a kind of a mystery in terms of an extra component and stuff that we don't know what's going on there. And we have tested some tubes. Most of them were good. There were some failures, and so I'm going to have to go and order those tubes or see if I have them in my stock, and then test those, of course, when they come in, and we'll see if everything's good to go. The next time you see me, we'll be talking about why capacitors go bad, and a little bit more on the electronics theory that I kind of promised you we would go through. So we'll do that next time. Be sure to hit subscribe or like or whatever you like there. As you know, that helps. And we'll see you next time. Bye for now.